And I'll just give a quick introduction for Dylan and for who we are. My name is Leon. I'm a developer relations engineer at Gnoland. We're building Gnoland. I'll hear a little bit more about it, not in too much detail because this is a educational perspective presentation. But Dylan here, my colleague, he's a senior developer in Gnoland, and he will help you out to understand what we're actually trying to do. Any words?
Great to be in Serbia. Let's get started.
Yeah.
Yes. Thanks for having me, everybody, and thanks for having the team here. This presentation is called Building Dynamic Applications with Go and Gno, which is kind of our own flavor of Go that we use to help us write applications that exist on the blockchain project we're working on. So, all right, so a little about myself. I'm Dylan, I'm a senior engineer at Gnoland. I think I'm a Go maximalist. I see other programming languages and I wonder why I can't do it in Go. So I've been in this Web3 space for the past 3 years, and I just joined Golang project 7 months ago in October. It's been great so far, really interesting stuff. Yeah, so when I saw this project and I joined the company, I was just really interested to see this concept of how I can write smart contracts on the blockchain using the Go programming language, which was, haven't seen anything like it before, so it was pretty exciting for me. So we have Gno and we have Gnoland. The former, Gno, is a interpreted programming language that is very similar to Go. The key difference being that it's deterministic, and inside of our Gno interpreter we also include, it comes with a data store that's bundled with it. And Gnoland is the blockchain project. So, people can write smart contracts in Gno, and then they'll be executed on the blockchain, and if anyone's familiar with it, reaches consensus. But it's a cool way of doing it as opposed to other languages that use Solidity or I don't know what Rust or Solana uses Rust maybe. But yeah, so it's pretty cool to be able to use a simple language like Go. It's not fully implemented right because it needs to be deterministic. So we don't include a lot of things that are non-deterministic, or anything really, I should say. And our version is based from version 1.17. That's the version right before Go introduced generics. And yeah, it's going to be a key part of our upcoming blockchain release. And we're going to be focusing really only on the Gno virtual machine and not so much on the blockchain project for this presentation. So what will it cover? We'll take a look at Gno, kind of its feature set, its high-level architecture. Take a look at how some things in the virtual machine work as well. That's what we call it, the GnoVM, or the Gno virtual machine. And then we'll kind of go through a few use cases on how Gno as a interpreted language can be used outside of the blockchain context. I don't know if anybody has computers here, or if anybody's interested. I did make a repository here if you'd like to follow along. If you don't want to, that's no problem. All right, so the kind of the key features of Gno, and that's determinism. This is kind of powerful because definitely is powerful in a blockchain environment because you need to reach consensus, but I think it also creates the opportunity to develop some interesting applications that maybe you wouldn't be able to in Go for that reason. And we don't support generics yet, as I said, because, well, we just haven't gotten around to it. It's a little bit more complicated than it needs to be. It was kind of a contentious feature when it came out, but we do have plans to support it in the future. No concurrency, as I said, so we're not going to have, you won't see things like Go routines, channels, no sync package, and that's fine. And another cool thing about Gno is we have this built-in application state persistence. And we'll go into that a bit deeper later, but in general, it means that when I'm running a program that I wrote in Gno, it can abstract away anything that you need to do, for example, to store things or read things from disk. And it'll just look at the global variables in your program, and when you read or write for them, it'll take care of that for you automatically. What it does come with is most of the standard libraries that are deterministic, we have managed to port over. We still have work to be done in that sense. And we also have included a lot of kind of example packages, or you can think of them as kind of like our own standard library, things that are written in GNO code that people that write GNU applications are able to import into their own applications that they write. And I just wanted to click on this real quick. We do have a whole page dedicated towards what we do support, what we don't support, just to try and make it transparent and easy for people that are interested in writing programs in GNU to understand what the current limitations are. So that is on our docs website. It's not too hard to find. All right, so the first key aspect of GNU's determinism is, so what are the differences with this? Map types are interesting, right? If anybody's familiar with how map types are implemented in Go, kind of when you're doing access, or rather when you're iterating over key value pairs, the order is not determined, right? It can change every single time, not something you should rely on. So in order for us to support map types, we had to change the implementation a bit. It becomes a little less efficient because we have to kind of change the implementation, but that's fine. We don't necessarily recommend using them all the time. We don't have none of the network package libraries are supported. And time.now is interesting because obviously it's non-deterministic. It gives you current time. But we kind of solved this problem in GNU land on the blockchain by including the block time inside of the execution context when we're executing GNU code. So we are able to get, depending on how fast the blocks are, we are able to get a fairly accurate timestamp. But if this is running outside of the blockchain, just on its own, the GNU language, we don't have a good way to support that. But towards the end of the presentation, I will propose this, an idea to solve this, and maybe solve other problems that you might encounter while trying to incorporate some non-deterministic features into your program. All right, so this is kind of the rough, highest level view of our virtual machine. The machine itself has 3 parts. First part is our preprocessor. This will do things like not only parsing, but a lot of static checks that it can do with the information that it has, like type checking and termination statement analysis. And if it passes those checks, you'll end up with this abstract syntax tree, which then gets passed into our execution layer. In our execution layer, perform operations, and we use various different stacks to help us manage values as we're executing each statement. And once execution is complete, we're left with this representation of the data that has changed inside of the virtual machine. That may be the data that we want to persist to disk or update or, in a sense, delete. So that's kind of our data lifecycle management, because we're keeping track of all of the references of the data that our GNU program is using, and we'll persist it. And when something has no more references, we'll just get rid of it. And it just writes to right now it just writes to a single key value store to keep things interesting. We'll get into the execution and the data lifecycle a little bit deeper. All right, so how does the VM work, kind of from a high level? So we have this AST tree that we are traversing the nodes of the tree. And these nodes are these statements that need to be evaluated. So we have expressions, nested expressions. So just like an example of a mathematical expression, right? This is kind of how we would break that expression up into sub-expressions. And as we're evaluating it, we're using different kind of stacks to keep track of our values. And these are the values that ultimately are marked at the end of execution that tell us, oh, do we need to persist this value? Do we need to update it or delete it? I did make this. Maybe if we share this presentation with y'all afterwards, I just was trying to kind of represent how our expression and value stack would be structured, and the differences for each of the steps that we'd go through just to evaluate a statement like does n mod 2 equal 0, or is n even, essentially. But we don't have to dwell on this. This is kind of not that great to look at, I don't think. And yeah, so let's move on. All right, so we have our GnoVM. This takes care of, it's essentially the execution layer. And we have 3 main entry points that people can use to interact with the virtual machine. The first entry point is I have some code. I want to send it to the virtual machine. I want it to evaluate and give me the result. It's just like equivalent of evaluating a function call or an expression, or even running like a main program, and just getting maybe whatever, for example, whatever the main program prints. The second one would be if we create a new app or package. Now, in this context, you can think of an app as like a persistent application that's written in GNO that when I create it and I have these functions on this app, I'm actually able to call these functions. It can change the state. I call a function again. It'll do that operation on top of the persisted state of that application. And the last thing, well, you know what? Yeah, I just explained both of them right there. So and it will send back a result to the client if this is a function that you're calling that does include return values. If there's no return values, it'll just say, yeah, it succeeded. That's good. All right, so here's like kind of the first hands-on component, or like an example, I should say, of this presentation. The goal is like, we're going to have 5 of these throughout the presentation, and it's going to incrementally build up to try and illustrate how, in my opinion, and hopefully after this, in your opinion, how GNO can be a useful programming language given both its features and kind of its lack of features compared to Go. So let me, this is an application that you might write where we can make our, sorry, that's fine. We can make our virtual machine essentially like embeddable inside of your Go program. So what this will do is it will create a new virtual machine. It'll read the program that will pipe from standard in, and then it'll just run it, right? And the input string here is just going to be the code. So what that looks like, let's see here. Right. Okay.
You missed .go, main.go.
.go IBM.
Oh, I missed that, didn't I? Yeah, thanks, guys. Okay, it just took a little bit there. Oh, look at that. So it says hello. That's pretty cool, right? So we made something that can print. That is, I got to switch my. How is this helpful? That particular example, maybe not that helpful. It's just running a main program won't get you too far, right? But the important thing to note, like what have we observed? You can run arbitrary GNO code inside of your Go application, which means I can receive requests and execute code inside of my Go application without having to recompile the binary or restart the binary. Just do it in real time. But it is deterministic. I mean, that wasn't that great of an example for determinism. I'm just reiterating this point, right? It is deterministic, and that is cool. So let's move on, and we will, yeah. Sorry. Thank you. Okay, so we'll move right into phase 2 here. This one's a little bit more complex. Here's an example of like what you'd typically see as a GNO program. This one's called adder. So it's a pretty simple concept. You have a value. So like I said, global variables will be persisted. So we'll add some arbitrary integer to our existing value, and we'll just keep a running total. Now, you can get the value at any point by calling this value function. So on the right, we have, you've already seen how the virtual machine can be kind of imported and create an instance of that in a Go program. This is just some basic command line thing that allows you to do 2 things. Create an application that'll create this, and call, in which case we would pass in something to add and then to value. So let's try that real quick and see what that looks like. So if I go back, There we go. Right. And I have the commands here for convenience. If I copy all of it. All right, so let's create that first one. So when you actually, because we're starting it up for the first time, and it's the first time like that this virtual machine is being initialized, it is actually creating this, this subdirectory here, and that's where the first time anything is started up like that, and there's no data directory that exists, that will create the data directory for you. So that one went through, all right. So at this point, our application has been created, and it's been persisted. Now we'll say I want to add to that, so I'll specify the app name, the function I want to call, and in this case, the single argument that I want to send to that. So let's run that. And I can copy the next one a while. Yeah, so that says, OK, that worked. And now I want to see what that value is. So I did create that value function as well. So let's call that. And now this function returns a value, so we should be able to see what our current value is. Any guesses? 2, right? That's what we expected. So yeah, so this was a bit, you know, I don't want to, I hesitate to use the word bit more complex of an example, but it was an example. So, all right. So we used the virtual machine in a CLI. We had this new app that we created that is persisted in our local data store. So every time we call any kind of functions like add that will be modifying, we're actually persisting state. But you know, in that code, there was no code in there that even alluded to the idea that we're persisting anything. And that's kind of a cool thing, because all I need to do is define my global variable in my GNO program, and this is built in for me. You know, persistence, retrieval, deletion, updating, etc. Let's take a little bit of a closer look at our application flow here. So in that previous example, we created the application. So what happens when we create an application? Well, in an earlier slide, I mentioned that one of the components of the virtual machine is this preprocessor. So that'll parse the code for us, do static type checks, and that'll produce kind of a few things for us. One, we'll have these any declared types that were in our program. We'll persist those to our key value store, because we may want to use them in other programs as well. Or next time it's loaded, we'll say, oh yeah, we have these types defined. Let's pull those so we know exactly what it is we're working with. And we have our application variables. In that case, it would have been like the variable that was holding the value that we were adding to. And finally, same as in Go programs, when you create an application, if you have an init function, it will execute that init function by sending the lines of code in the init function to the VM, and then executing it and saving the results. Ideally, like if you're executing an init function, you're probably making some changes to your global or stateful variables. And then we called the application, one to add and then to retrieve the value. So what does that look like from a high level? So we make the call. It loads the package from the store that was in the kind of that subfolder I showed you that got created. And again, we'll do pre-processing again, just to get our tree ready for execution. We'll execute it, and then after the execution, we'll 1, store the values, and 2, send the values that were produced back to the caller if any values in fact were produced. Now, like what's special about this value persistence? Yeah, it's automatic, right? Like in Go, I don't know, like if I want to write a file, I have to say, save results to this file. And that's kind of a common pattern. But anytime I write an application with GNO that looks almost exactly like Go, I don't need to concern myself with that. It just happens automatically. It's managed, right? Like I mentioned before, we have this life cycle. We're tracking all the references to all the values for everything that we're persisting. So anytime that we update a value, it gets saved. Create a value, it gets saved. We maybe we'll change the references around a little bit, and maybe one of those values that we were previously storing now has a reference count of 0. So we know nobody's referring to this anymore. We can just delete it. So it's kind of like garbage collection in a sense, where we just get rid of everything that we know isn't being referenced anymore. And it's kind of neat, right? So the state persistence, how do we determine what needs to be persisted? Well, first way that we kind of start this whole process is we do some kind of assignment. We're doing an assignment to a value that we currently have persisted. So we'll take a look, we'll get the existing object, put it here, and we'll say, okay, let's do the assignment. If it has a parent object, we'll say we should mark you. Your child was updated. We're gonna mark you as dirty because it's possible that this value is actually a part of the parent object. They might need to be persisted together. We'll mark the object that was created as new, and potentially mark the old one as deleted, right? If it has no more references, or rather, at least decrement a reference count so we can later mark it as deleted. And we'll kind of go to enter our data finalization process after execution, where we'll look at everything new, updated, deleted, kind of comb through the references to build a finalized version of the steps that we're going to need to take. And that includes recursively processing maybe child objects if this is a piece of structured data to find everything that does need to be updated. And at the end, save the values, update the values, delete the values. And a little bit how we structure this. So it is a key value store. And each of these objects, you can think of an object as pretty much any, well, here we go, I'll tell you. Each one has an object ID, that's kind of that's the key. And then think of objects as being types like arrays, structs, maps. These are kind of your more complex objects. And we have something called a block, which is kind of like in our own execution, or in our own, what's the word I'm trying to say? In our own view is just a block of code, like you're executing, like if statement would be a block, for statement would be a block, et cetera. And why these are the only ones saved are because pretty much everything else in our, in the way that we represent data in GNO can be represented by one of these. So a slice, right? Well, what is a slice? A slice is just basically, underneath it, it's just represented as an array. Now you say, well, what if I have a global type or a global variable that's a primitive, like a string or an int? Well, that is like the highest level block of code, right? So we'll just have a list of values, and so that'll be persisted as a block, or fields in a struct, If they're just primitive types, it would just be a struct with a list of values, so they just get persisted as part of the struct. So these are really the only types we need to persist, which makes it a bit easier. And yeah, okay, I think I covered that. So there's just a small example of how things would get persisted. So we have the info struct here, right? We have the full name struct here, which is the type of one of the fields in info. So here's what happens when you set a variable in GNO. We call set info. We create a new instance of an object, info object, that includes a new instance of a full name. So what happens here is if we have this object, so that's one object we're going to need to persist at the end of execution because this is a global. We also have this full name object, which isn't a global, but it is part of a value that's being persisted globally. So we'll want to persist that as well. So now we have two objects. Like I said, these are just primitives, so these are actually included in the info object when it gets persisted. And another kind of something that might happen is if we update it, right? So here we're updating the value of this full name. So what that means is we're not overwriting it. We're not creating a new instance like we did here, right? So we can that would just end up getting marked as dirty, and then rather than any other objects actually being created or destroyed, we just save the results. So now you can imagine like more complex scenarios, right? Like if we had a very deep nested object and we update something down here and we say, oh, okay, we've updated it, we didn't create a new instance, that needs to be deleted. And then the parent object will say, okay, this is going to get updated. But now, maybe halfway in this deep nested object, we delete that portion altogether. So we had something that was marked as we need to update, but now one of the ancestors was deleted. So then we have to figure out, when it comes to persistence, well, this was marked as needing to be updated, but what else was updated, what else was deleted? It's not super trivial, but it is pretty cool because it allows us, when it's implemented correctly, it allows us to offer this kind of functionality for anybody developing GNO programs. Okay, phase 3. So the goal here is, so far we've been working on the command line, and we thought, well, it might be kind of cool if have like a UI, right, in order to interact with our application. So let's take a look at that, what that might look like. So we'll go into, oops, got to go back one. All right. Okay. And we'll start that up. So what this is going to do is it's going to give us a web interface that instead of doing everything through the command line, we are able to do this through the web interface. So local host 4591. Okay, so this is pretty simple, yeah. The cool thing about that page that you're seeing right there, sorry, let me just copy this code real quick. The cool thing about what you're seeing here is this is a GNO application that was executed to produce this web page. And this is an application that came bundled with the VM when you started it up. So let me paste in a GNO program there. It's called myname, which has this function called render that takes a string and it returns this value, says my name is, right, argument. So let me create that. Okay. So after you create an application like this, we can do something, instead of installer, what do we name that package? My name. So we can do my name, colon, type my name in there, right? It says my name is Dylan. Well, that's okay. That's kind of cool. But let me explain exactly what is happening behind the scenes here. So once the app was created, it allowed you to access that through the browser using the application name. That render function that you saw has this signature, a func that takes a string and returns a string. This is something that any application that includes this function in its code, when you can visit that on the web, it will. That's where you could return like a user interface for the user to interact with. So and you notice that there was like a colon in the URL path. That's just a convention that we currently use for delineating the argument that we want to pass in to render, which then upon execution it can read that, interpret it. It could even be used for potentially like a kind of routing for your application. To route, if you type in the full path in there and it can route to different logic as you want to do. In our case, this render function for the installer actually returned HTML and JavaScript, so that when you click the submit button, it kind of called back into the HTTP server we had running with our GNO server, and it was able to create the application that way versus creating it how we did before, just through the command line or just having it hard-coded in there. And I don't know if you noticed, but there's another interesting use for this. So when I started that server up, it was on port 4591. And in that code, it actually, it said, I want to create this port app as well. And the reason for that was, think about this. When I'm serving code for the installer app, for example, I don't always know what the port is that I need to call back to on the server that I have running. So if I have this, if I can bootstrap off of our GNO system and write a port application, every time the application starts up, I can actually update that port number using set, and then the installer app can import this application, call number, when it's rendering the output to send back to me. So that HTML code or JavaScript will always know exactly what port my server is running on, because when I started it, I set this, and it's persisted in storage. So that's kind of neat, and we'll see maybe at least one or two other things like this where you can kind of manage your configuration if it's configuration that is used by multiple other applications that you have installed on your virtual machine. All right, so that last part was kind of cool, but if I want to run an application or write an application, maybe I don't always want to have to copy the code, send it to somebody, and have them paste it in their browser. I may just want to kind of like self-host it in a sense, where I can download it and install it automatically. So let's take a look at what something like that might look like. Okay, so here we have the famous Alice and Bob. Let me just go back here. Okay. Whoops. So I can start this up. And now, so Alice is running. Now I can start up. I might not went back far enough, or I spelled it wrong. Whoops, sorry guys. Where am I? I'm on, okay, cool. Let's go to phase 4. CMD, Bob. Right. And I'll start him up. Okay, perfect. So now I can use the same code that I used before actually for this little application. And I'll go back to Alice here, to her installer. She's running on 4591. I'll go back here. I still have that application. Let me create it again. This is in a new folder, so it's a new data store. And now let me go go to Bob 4592. Remote installer. And now Alice said, well, Bob's a friend of Alice, so he knows her address, right? Which is 4591. And he knows that he wants to install this application that she's made called My Name. So we'll say, okay, I want to get that one. So now he can go to My Name. And, well, he has a name. It's Bob. All right. So that's, sorry. That's kind of cool. It's not only do you have to always write applications and install them yourself on your computer, you can actually source them from other people. So how does that work? Well, we have this, this virtual machine interface that I was talking about earlier, that you can create packages, you can run arbitrary code, you can call functions to return values or to make state changes. And we can add a couple other methods on there to query a package and to create a package, which, a mem package is just kind of like an application. It's just strictly the code and a few other data items that you don't really have on your application when you create it. So here's kind of how this works. We have our client, which was basically me in the browser. I said, I want to install this remote application. So I sent it to my locally running server, which then took Alice's address, routed it to her machine, says, hey, do you have this app? I'd like to have it. She said, yeah, I have it. sends it back. Now I have the application, and I can install it on my locally running VM and get the result back. And it's also going to have all the, if it's a stateful application, now Bob will have his own version of that stateful application. Not a copy, it won't stay in sync, but it will have all the same functionality as Alice. So maybe we can take this, there's one more phase of this arc of examples. Maybe we can take it one step further. It would be nice if users could interact with the same app, meaning if Bob installs something from Alice, or if I install something from Alice, I would like to use that application from my computer, from my web UI or whatever, but I'd also like the state to be synced for all users of the application. If I do something, I want Alice to see it. If she does something, I want to see it. So let's consider the simplest case. We have an application with no other dependencies. Need for security, this is just an example, so we won't worry about security either. Maybe we can do something, something event-based. We do have this virtual machine that we can execute these kind of arbitrary calls and events, and it's deterministic, so that means we're always going to produce the same result no matter where we execute it, as long as we do it in the same order, right? And a cool thing we can do if we're doing anything with events, we can also even bootstrap event storage on top of our virtual machine, meaning we don't have to figure out how we're going to, maybe how we're going to store the events, but we don't have to figure out where we're going to store the events. We just have to define a data model and make a call to this event realm, and that will do all of that for us. So let's think of a simple event storage model that could be used for kind of solving this kind of problem. Here would be like an interface. We want to, sequence is important. It tells us the order in which to apply events. Store, that's important. That'll store an event, right? And then get, so like if I fall behind or I'm just want to get a specific event, I can give it a range. I ask Alice, hey, I missed the last 10. Can you send them to me again? She goes, yeah, sure. She'll send me those events. And we'll probably want to do some kind of like a JSON encoded string, because when we're getting events remotely, it's probably would be good to have it encoded in something like JSON for just like structured transmission. And here's kind of the architecture that I just described. I mean, this is all just an example, but so we have our HTTP server that we had running earlier. Both of us do. That's mostly for if I want to call a remote app or install it, request a mem package, receive a mem package, that's for installation. We have our VM, which when we install the mem package, and it'll store state as well. And we have some, probably some WebSocket client and server. So if I install a remote application and Alice makes a change, I want to be subscribed to that application. I can retrieve those events after she executes them and applies them. And I can send them to my own virtual machine, apply them there. And now that way we can kind of keep in sync. And over here on the remote application, you can see I can receive requests for events, I can return events, emit events, and all the while always applying the same state changes on its own, onto its own key value store before broadcasting them to subscribers who want to keep their own applications in sync. And okay, so this is the last, just like the culmination, I guess, of my examples. So in this example, what we're going to do is we are going to have Alice create an app where she says that allows people to post something like a board, and hopefully, hopefully other people can post something as well. So let me just go and start up these servers real quick. Phase 5, MD/. Okay. Yes. Phase 5. Okay. . give that a minute. All right, cool. So I actually have a Postman collection for these because it's a few requests and it just makes it easier. So, all right, so first we'll have Alice create this app. Yeah. Okay, whatever. Well, Alice create this app that it's hard to read because this code isn't formatted, but I'll tell you what it does is that it'll take a string, it'll post something, and then when you call render, it'll render the entire contents of everything that's been posted in the browser. So let's do create. This sends it to the server, her local server she has running on that 4591. Okay, we've created an app before. We know what that's like. Now Bob says the same thing we did earlier. He installed a remote app, so let's do something like that again. He's going to install the app that she just made, post it. Now Alice says, okay, I'm going to post something. So there's first post. Okay. And Bob says, this is him coming, posting to his now, 4592. He said, I'm going to post something, talk to my VM and say I want to post something as well. And then finally, we can have her post one more thing. So what does this mean exactly? If we go back here, we're on Alice now, right? 4591. Let's go to that app that she just created. Post it. Okay, she has the history. Now they both posted. They both, they sent these requests to their own. The request came in through their own like HTTP servers that are running on different ports. But Alice has the thing she made, the thing she made at the end, and the post from Bob in the middle. Well, let's just check. This is a little bit funny. Let's just check to make sure that Bob. Okay, so we just rendered the same, made a call to the same application on Bob's VM, or server running the VM, and when this was rendered, it didn't call Alice and ask for her data or anything. It already had all of that data in its local data store because he installed a remote application and it was syncing, listening, subscribed to the events coming over. So anytime there was an application state, he gets updated. He can still retain a local copy of all of the data that is associated with the application. So that's kind of neat. How does that work exactly? So I think I just explained how it worked, but these were some improvements that can be made to this kind of thing. Like this was an application in which I thought of how can I go through different phases and try and convince somebody that there is some kind of utility to using a language like GNO to execute arbitrary interpreted Go code essentially on your own computer. And I think the answer to that is to build an application like this that allows you to layer things on top of each other after you've included the GNO virtual machine into your own Go application. So some things that can be improved. What would make this better, right? There's a lot of things that would make it better. To start with, better event syncing, like catch up if Bob gets behind that hasn't been implemented. Failures and retries, maybe a reputation or some kind of pseudo trust system. Maybe using the blockchain as a source of truth for various different events that can happen inside, or very different functionalities of an application. As well as maybe like some whitelists, trying to prevent spam and data encryption. I might interact with an application. I want to share some things, but not all things. If I want to keep it stateful, I still actually have to have that state to make sure that next time I apply an event, I end up with the same result as everybody else. So maybe there's a way that we can do something like that with encryption. And the last thing I want to touch on before I let you all go is I did mention earlier about time.now and how in the GNO context outside of the blockchain, there's really no way to make it deterministic. There's some other problems like this too, right? Randomness, generating a random number, fetching data from third-party services. They are non-deterministic operations, but when we're no longer on the blockchain, we can actually split up these kind of requests. Like if I have an application that has something in it that requires the current time, if I want to make the call to the application, we can always split this up into two steps. We have some some step outside of the virtual machine, which can give us the current time, produce an event, write it to our application, and then do the call, right? Because when I do that call, I have the latest time on the virtual machine storage. That means that instead of, if I want to make one call to this virtual machine, I'm not actually producing one event like I would normally. I can actually produce 2 events, and it's those 2 events that could get sent to everybody else. And it's those 2 events that, when applied in this order, will make sure that everybody else actually produces the same result without having to, they don't have to get the current time, or they don't have to come up with a random number, because it's part of the event sequence that led to the completion of kind of the action or the function call that the caller initially intended. So the kind of the key takeaways from this, right now, GNO is only really used as part of GNOland for writing our applications, or the contract applications rather. We are starting to think about ways and work potentially coming up with plans to do something akin to this, not exactly like this. This is just an example that I built, but something that does kind of give the GNO language utility outside of the blockchain context. Again, just to really hammer these home, the key kind of advantages of using GNO is its determinism, storage capabilities, and even like bootstrapping rather various configuration and kind of full system or application state on top of the GNO storage system itself. We saw event storage. We saw that kind of maintaining the current port number of the running application server as well. And in the future, right now, because we come from a blockchain space, we have a lot of things that can't be undone, right? We can't. There's no way to remove an application currently, but it is cool that you can kind of apply these changes to your application where the VM is embedded inside, and you don't have to restart your binary or recompile, and that's what really makes this. A way to build dynamic Go applications, right? Because you have your static Go binary, and the dynamic part of the application is the interpreted GNO code that can be included or accessed through the embeddable virtual machine. And that's it. Here's some links that you can, if you want to find out more about us, and please scan this QR code and maybe get some feedback on the content of the presentation, as well as maybe, drop us a line or something. So thank you very much.